Hi, my name is Stephen Feng, and I'm proud to present our project to you with my teammate Tao Zhang and Chu Yunshen. The topic we want to tackle is optimizing the processing of COVID-19 tests. In some of the hardest hit regions around the world, the bottleneck of COVID-19 testing is often not gathering data, but processing them. In certain regions of US, for example, samples can take, on average, up to 2 weeks to process. On a personal level, this means individuals with mild or no symptoms could be going to public spaces, beaches, parks, and spreading the virus for 2 full weeks unknowingly. And for those that have a weaker immune system, they could potentially face hospitalization or even death. We want to reduce the processing time and by extension, lower the spread of the deadly virus and prevent death. A technique commonly used is pool sampling. In essence, instead of testing samples one at a time, samples are being tested in batches. Individual samples in the batches will only be retested if the batch returns positive. As seen here, pool sampling could vastly reduce the number of tests compared to conventional methods by up to 70%, and this is not coincidence, this is a common occurrence. This technique has the potential to be very effective, but only with the most optimized batch size. For example, in South Korea has an active rate of approximately 2.5% and takes around 15 tests with batch number of 5, whereas in Philippines, which has an active rate of 14.5%, it requires 40 tests with a batch size of 5. So this shows that the effectiveness of pool sampling technique depends heavily on having an optimized batch size for the active rate. The paradox is that we can't determine the optimal batch size without the active rate, and we can't get the active rate without testing the samples first. And to solve this issue, our solution is AI. Our product feeds data from Johns Hopkins University, that COVID-19 database, which means we can get testing and active data around the world where available. Our sophisticated neural network accurately predicts the active rate of the coming days based on past data, and we use algorithm to determine the optimized batch size for the coming days in each region to achieve the best processing time. Our data is automatically updated from Johns Hopkins University and the Government of Alberta website and are being updated daily.
So to predict the optimal batch size, we first use neural networks. We use recurrent neural networks in TensorFlow and Keras, which work best for time series data. We take the previous testing and infection data from a 14-day window, and we want to predict testing and infection rates for 7 days in the future. We also train on new data every day as it comes in. As you can see on the left is our network. It has 3 hidden layers, 2 LSTM layers, and 1 dense layer. To get our batch size, we repeat our predictions iteratively to get a prediction for 7 days into the future, and we use testing and infection rate to get the optimal batch size using this paper. And this is just some of our plots of our predictions for California. As you can see, testing per day more or less continues the same trend. The new cases, it follows sort of the same trend, only averaged out a bit, and the initial batch size more or less follows the same trend. You can see this for New York as well. The predicted values sort of continue the original plots, and the new cases only averaged out a bit more.
We see a great opportunity in this technology since an optimized pool sampling technique significantly outperforms conventional technique. So there exists a demand for a solution like ours to provide an accurate batch size estimation. We have compiled data for all 50 US states, territories, and Canadian province Alberta, and we hope to provide it for free to increase test capacity. So now I'm going to pass this on to Chu Yun, who will do a demonstration for our project.
With our application, we are able to first select the location. Here I'm going to demo with Canada, Alberta. On the right hand side, we can see the actual data in Alberta. Purple represents active cases, whereas orange represents tested cases. Our algorithm in the backend calculates the best performing prediction batch sizes. With those batch sizes, we are able to see the predicted data in Alberta. The predicted data in Alberta are represented after the purple line, present day. How we calculate these numbers is through a certain procedure. We first divide our COVID test samples into batches of a certain size and test each batch on if there are positive COVID cases. For each group that shows a positive output, we divide these groups into sub-batches of another size and subsequently test each batch. Then we iterate the process once more to obtain more sub-batches with positive COVID cases. Finally, for these sub-batches, we test each sample to single out the individual cases. And we have another plot to represent predicted percentage in Alberta, as you can see here. And we can zoom in.
Thank you for watching our video, and we hope you enjoyed it.